University, Israel.
Okay, thank you. Okay, so I'll share my screen.
Yeah. Please share your screen, doctor.
Yes. Okay. A moment. Okay. From start. Okay. Thank you very much for invitation, and thank you very much for chairperson for the opportunity to give the talk. Okay, today I talk about characterization of graphene oxide single layer, and in the beginning of my talk, I will give a very short explanation about difference of graphene and graphene oxide. Actually, today, Professor David Moss already discussed this subject, so it will make it very short. And after that, I will talk about open question about regarding oxygen debris that organize on during the process of graphene oxide production. And I'll discuss with STM and STMS measurements, which we characterize our sample that was deposited on substrate, on gold substrate, and show the previous experiments and show our results and discuss and conclude my talk. Okay, so graphene is a single layer of graphite, and well known, and was practically was experimentally achieved in 2004, and in 2010 it was get the Nobel Prize to researchers from Great Britain. And this single layer have many different excellent properties. However, practically for industry, it's pretty difficult to use because of usually it's take from a mechanical exfoliation that sizes is very small. It's not can be industrial. Can become repeatedly achieved, and also though it's difficult to make on the large sizes, large production. So another idea is to perform graphene or making some, for example, it's what's called reduced graphene oxide through producing graphene oxide, which is taking a chemical exfoliation instead a mechanical one, and this comes with oxidation of graphite, and we get graphite oxide, which is layers of graphene connected with oxygen groups, and but these oxygen groups make weaker connection between the layers that already is not such strong. And if we make a different process like sonication, chemical or thermal processes, we can separate these layers and achieve graphene oxide, which is a layer of graphene with oxygen groups. So so now question is what's going on during this process? If this process is so clear, clear, and this process is clean, we get this graphene oxide, like it's showing on this on the theories with models would describe this process. And unfortunately, it's not so, usually it's not so easy. The process is not so clean. And many times during the process of chemical encapsulation, we get some residual clusters that comes from the fact that during the process, oxygen is connected with and during oxidation and during the sonication processes, we have clusters of oxygen groups with carbon, or even carbon and OH groups, and we get that's what's called oxygen debris that it's mostly prevent to make this sample is pretty dirt, and it have to be cleaned. So the question is that we want to ask and want to do in this research is what is the reason of this oxygen debris? What they come from, and if it's possible to reduce them with some simple procedure, and if we possible to make a single layer of graphene oxide or reduced graphene oxide, which is will be similar to graphene. Okay, we want to make a study of this process. So in order to study this, study electronical distribution and also morphological spatial distribution of this material, we perform scanning tunneling microscopy measurements. Scanning tunneling microscopy measurements, which is can do on the in this equipment. We measure tunneling of tunneling current coming from the sample to tip, and we are measuring also. We can also if we have conductive material, we get different, we can go on the constant voltage or constant height from the sample and get also like microscopy morphology of the sample. And moreover, if we make differentiation of this signal, we can get changing of this current as function of voltage, and this is similar to electronic distribution on energy levels of the material, and such we can such way we can measure a density of this density of states for this material. So in the previous work, it was done in two ways to study influence on the scanning tunneling microscopy, studying distribution of oxygen groups on graphene oxide. One type of measurements is done when it was checking actually graphene oxide, which is actually multi-layer. It's not similar single layer graphene. It's at least number of layers that stuck on each other. And when performing scanning tunneling spectroscopy, they show that have band gap that show that is not actually the band gap shows that it's not graphene. Okay, it's more like a graphene oxide with a band gap. It means that We don't have Dirac point, we have a band gap, and moreover, this band gap have additional energy levels or oxygen groups levels, and okay, and this not because of this band gap is pretty big, and we have many energy levels, oxygen levels inside this band gap. That from one side we can't fix them, can define which energy levels we get, okay, because it's smeared on this band gap. But from other side, it's not dependent on the place. You can measure in different places on the sample. In average, you get almost, as I see, almost simple, similar graph of energy band gaps. From other side, different experiments was done when it taken pure graphene, okay, which is achieved by mechanical exfoliation, and it was input immersed input on the top of this graphene, single oxygen groups, okay, in some particular places, and after that it was measured STS measurements as function of distance from these oxygen groups, oxygen atoms, and it was shown that the STS measurements and density of states is changed very drastically. For example, if you go into single graphene, we see we're starting to see here like a V shape, and when we going closer to this oxygen, we get smeared like similar that we get when in a multi-layer, like very wide curve with energy gap inside. Okay, so this is a previous work, and we started to make this measurement, and in order to make it, we need to, first of all, we take to find a substrate that can be conductive in order to perform STM measurements. And also with very low roughness. So we take gold was grown on mica, and we used drop cast method to put our graphene oxide. We use industrial graphene oxide and perform measurements. In the beginning, we take graphene oxide, which was multi-layer, and we see this, we get clusters with weight of about 10 nanometers, but measured by atomic for microscope measurements. And we also measured Raman spectroscopy and XPS spectroscopy in order to see that we get spectrum of graphene oxide. And then we go to STM measurements and STS measurements, and we see, first of all, on energy measurements, we see that it behave like we see on previous work experiments. Then we have multi-layer, we have band gap, and this spectrum not depends on the place where we are measuring. But now, in addition, we make STM measurements, and we perform Fourier transform of these measurements, and we make analysis of this Fourier transform, and we see that we see very clear two types of points on this Fourier transform. First of all, we have hexagonal shape that we connected to pure graphene oxide, pure graphene pattern, And inside with low frequencies of which we close to zero, low frequencies, low spatial frequencies of in Fourier transforms, that it's connected to oxygen debris that we was called. And moreover, when we make filter out this central part that was reflected to oxygen debris, we see that our pattern actually it's in their Fourier image. Okay, we see that it's very clear. It's even seems very similar to pure graphene, and even distances is reflected to pure graphene. It's not have distorted, almost not have distortion or defected. Okay, and this was very nice. Then we think how we make a single layer graphene, how we can do it. So it's actually when you take industrial, that was bottles that we get from the company that sell us this graphene oxide. And this actually single layer graphene is diluted in ethanol. And we can't, in order to get single graphene, we can make sonication process. And the sonication process, we separate between single layers flakes. And we also make dilution that reduce the number of flakes. However, it seems it's have to be a number of flakes is connected to each other. Okay, and because of this reason, we get multi-layer. So we make a small dilution, and also we have started to make sonication process, and we look what's going on if we perform first of all perform AFM measurements and see how it looks when we make sonication. Like we make sonications that reduce 100 density of these flakes. Okay, and also we perform 1 hour sonication. Okay, we make sonication about 1 hour of this from original solution, and we see that it seems in some way pretty clear. And we see that in this process we reduce, for example, in some places we reduce some flakes, we reduce the H, but no, and this was not enough. In sonication, well, for 1 hour sonication, we almost get a single layer of graphene oxide. So so we take this some flakes that we go into close to 1 nanometer and perform a high resolution TEM transverse electron microscopy measurements. And these measurements we did after 1 hour of sonication, and we get this very nice picture that we see that actually also other researchers succeeded to get it, that you see this clear pure graphene, and on the side of this, on top of this, we get these clusters. This look like oxygen debris. And even here, if we perform Fourier transform separation, we see that we have for pure graphene we get hexagonal, but for this distortion for this oxygen debris, we see a frequency close to 0, but it's not like it was in the multi-layer. It's less. You see some high points on this starting. It's the wide distribution, but it seems some peaks on this oxygen debris. Moreover, its XPS measurements started to be changed. Oxygen of percentage of oxygen is started to decrease. So we understand this is the way that we need to have to go. And after we perform the measurement, we started to make, after make sonication, we deposit our samples on the gold substrate, and after that we perform water rinsing. Interestingly, that this graphene oxide is attached to the gold, and this it have to be probably van der Waals connection. However, in some way, after water rinsing, not all flakes was removed from this substrate. Part of them is saved, okay? And this we measured these saved flakes, and we see that height of these flakes is removed even more. You see, it's removed even more, even below 1 nanometer. And after we do it, we started to perform again STM and STS measurements, and it was very was surprising us that we achieved almost clear reduced graphene oxide. Okay, we achieved the reduced graphene oxide that was achieved without make some drastic or chemical or thermal reduction, which usually perform defects on this graphene oxide substrate, on the graphene oxide material. And we get that we have some defects, and we see some distribution, but almost it seems like pure. And also even this curve of STS is in parabolic, it starts to closer in relative to multi-layer, and it's still not V-shaped, but it seems that it's going in this direction. On XPS measurements, we get this the oxygen peaks almost reduced totally. So we compared between different XPS measurements with one with F purchased, actually the original solution. That second is after only sonication, and third one with sonication and water rinsing. And we see that a single layer that was achieved after sonication and water rinsing, it's close to almost pure graphene, close to reduced graphene oxide material. It's about 14%. Yes, it's of oxygens. It's pretty good. Even that we have not perform some drastic reduction processes. In addition, we perform FTIR measurements and compare our results with FTR measurements. We see the components of different function groups that we have on this material, and we see also in FTR measurement we see a drastic reduce of these oxygen groups after sonication and rinsing process. So we believe that that what we did, that if you have a material that in some way these oxygen groups organized in clusters, that's what's called oxygen debris. Probably it's because, for example, it's soluted in ethanol and not water, or some different solutions that start the process of clustering of these oxygen groups. Then after the position of the sample and water reading, we succeeded to reduce these oxygen groups and achieved almost pretty clean reduced graphene oxide material close to graphene. And this process is very, seems to be very cheap and very straightforward. Still, we have many properties that not so clear. For example, how this materials is connected to the gold, and if it's possible to make for different materials. We did also make only on solution in ethanol and not in some different materials. So it's we can proceed on we're proceeding with this research. And okay, this is actually what I want to say. This was this is the result. Okay, so I'm not already talking this by my words, so I continue to acknowledgements of different people that will participate in this research. Actually, this work was done with Professor Frat Lifshitz group in Technion in Haifa in Israel. And with Orit Livni, it was students was from a lot of the work, and Dr. Sisi Salgi was responsible for working with STM measurements, and Kamir Wenfeld with XPS measurements, and Yaron Kaufman with high resolution TEM measurements. Okay, thank you very much for your attention.
Thank you so much for the wonderful speech, Doctor.
Thank you.
Now the stage is open for questions. We assume there are no questions for you as of now, Doctor. Thank you once again for this. Please